Hi, my name is Joe DeMonte. Welcome to the three-part series on infrared science. Our three topics today include what is infrared, what is emissivity, and finally, what is an infrared window and how can it benefit your facility. Our first topic, what is infrared? Infrared is a form of light. We're all familiar with the light that we see with our own eyes, visible light. Now, all light, as far as our science is aware of, travels at the speed of light, which is about 186,000 miles per second. The type of light that we're used to seeing comes from light fixtures, the sun. For instance, the sun shining on the planet through outer space, through the window, the light fixtures in this room that are lighting up everything that we can see. But most of what we see in this room is reflected visible light. What would happen if you turned off all of the light fixtures, close the blinds or shades in the room that we're in right now, and don't allow any light to be emitted into the room? It'd be total darkness. You and I wouldn't be able to see anything. Infrared light is very similar to visible light. It can be emitted by targets, it can be reflected, refracted, it can be absorbed, many different things. But the big difference between infrared and visible light is the wavelength that it's emitted at. Infrared is at a wavelength that's outside of our normal vision. We can't see it. However, infrared is also going to be traveling at the speed of light. Like I said, it's very similar to visible light. The big difference, however, in wavelength is the fact that infrared is longer outside of our vision, longer in wavelength outside of our vision. You and I are familiar with visible light being able to penetrate a lot of different things, such as a piece of glass. Now, a piece of glass and a visible source of light, a flashlight, the piece of glass and the flashlight really doesn't have a lot of absorption or attenuation of the visible light. We can see through a piece of glass with our own eyes. And the infrared side of the spectrum, infrared light that we use for maintenance today, commonly referred to as long-wave infrared, infrared light coming over here to our camera at the speed of light. Now what we're going to do is just take this same piece of glass and place it in front of the infrared camera. At this point, you can see that the infrared light from my hand does not penetrate the piece of glass. So infrared light, although similar to visible light, does have some differences. Every target that has a temperature above absolute zero will be a source of infrared light. That means that everything in the known universe is giving off infrared light. And the higher the temperature of that target, the more infrared it gives off. So the application for infrared science is manyfold. We can use infrared to do anything that involves us looking for a hot spot or a cold spot, anything that has a difference in temperature. And an infrared camera does not have to contact that target to measure the temperatures or see where there's something warmer or colder than it should be. The different applications that we're going to be able to use infrared for, and the applications that it's commonly used for, include energized electrical switchgear. While the switchgear is actually on, we can take an infrared camera, safely open up the switchgear, or use an infrared window to be able to view through it. We'll talk more about an infrared window in section 3, but as we already saw, a piece of glass is not going to allow the infrared camera to see into the switchgear. Therefore, we have to use special materials. But electrical switchgear and energized electrical switchgear is one of the biggest applications on the planet right now for infrared. Another application is motors and their associated driven equipment, like a fan or a pump, anything that has bearings or warm areas, just to see if a bearing is overheating, for instance. Another application that I've commonly seen and used over my years of experience is looking for weaknesses in insulation, whether it be a building or even your home, looking for heat loss. The infrared camera is so sensitive that we can pick out a very, very small temperature difference. The camera that we have in use in this video is able to pick out temperature differences as small as 0.08 degrees Celsius. If I take this infrared window, the cover is shut right now. meaning that the infrared camera is only going to see the surface of this cover. But I want to use this as a demonstration to show you how sensitive the infrared camera is. I'm going to take this object and then just lightly touch it with my hand. As I touch it with my hand, we're going to see how sensitive the camera is. The slightest touch of my hand has only increased the temperature of this cover by a degree, if not less. But again, the camera is sensitive enough to pick that out and see even that slight temperature rise. Again, the warmer a target is, the more infrared it gives off. And our infrared camera is designed to see what the human eye cannot. And it's perfect for the application of energized electrical maintenance. Our second topic today is emissivity. If you've heard about infrared science before, if you've learned a little bit about infrared science in classrooms or through TEG Corporation, you might have heard the term emissivity before, but what is it? What does it mean? The camera itself does not detect temperature. The camera detects infrared light. And a target gives off infrared light only as well as its efficiency to radiate is. And that efficiency is called emissivity. The higher the emissivity, or efficiency if you will, the better it'll radiate. Now, a properly calibrated infrared device such as the FLIR camera we're using for this demonstration can be made to measure a correct temperature. If your emissivity is set correct, you get the right temperature. If your emissivity is set incorrectly, you're going to have the wrong temperature. In this next demo, I'm going to show you how two different materials, which are at the exact same temperature, can look very different to the infrared camera. A simple heating plate, and on top of the heating plate is a block of aluminum. The block of aluminum has been heating up here for several minutes, actually probably closer to a half an hour. Our infrared camera is pointing to the target, which is the aluminum block. The target is giving off infrared. As we discussed in section 1, everything gives off infrared light. And the hotter this gets, the more infrared it's going to give off. A calibrated infrared camera, such as the FLIR in front of us, a calibrated infrared camera could take that infrared and physically give us a temperature reading. At this moment right now, it's reading about 107 degrees. At 107 degrees, a person such as myself should be able to come over here and pick this block up. I'm actually getting slightly burned here by touching it. Now, I'm not touching it long enough to actually burn myself, but I know that with the simplest touch, it's extremely hot and very uncomfortable to hold on to. My bet is that it's over 140 degrees. Well, why doesn't the camera tell me that it's over 140 degrees? The subject, again, is emissivity. Emissivity, by definition, is the efficiency of a target to give off infrared, or the efficiency of a surface to radiate. This target right here has a very low or poor emissivity. It does not want to give off the infrared that the camera desperately needs to give a proper temperature measurement. However, on the back side of this target, and I'll use something where a piece of insulated cardboard to move this. On the back of this aluminum block, I've placed numerous vinyl stickers which have a much higher emissivity. Now the camera can already see that these vinyl stickers appear to be brighter than the aluminum. They are brighter than the aluminum to the camera because they emit or give off infrared at a better efficiency. They have a higher emissivity. So even though the vinyl tape is the same temperature as the aluminum, to the camera's mind, they look much higher in temperature. Actually, the vinyl stickers are the correct nature and the correct temperature to the camera.
Yeah, go ahead.
On the strips of vinyl, with an emissivity setting in the camera of 0.95, I've got a temperature reading of 167 degrees Fahrenheit. If I were to move that spot over to the aluminum, we see that we drop back down to around 110 degrees. The vinyl, 167, 168, the aluminum, at about 110, 111. Which is the true value? The temperature measurement on the vinyl is the true measurement. The temperature on the aluminum is false because of a change in emissivity. In truth, the aluminum is every bit as hot as the actual vinyl. But infrared devices have to have the emissivity setting correct to be able to measure the object and tell what temperature that we do have. The cameras that we use, the FLIR cameras, have emissivity adjustments and an emissivity table built into them so that we could go through and pick the correct emissivity. The fact is that all the different materials out there have different emissivities. Whether you're trying to measure temperatures off of stainless steel or nickel or brick, each material has a specific emissivity that you must know and dial in. Again, training and certification is critical for the individuals out there using these infrared devices. An infrared camera is extremely accurate when used in the correct hands. However, an untrained individual can get extreme errors if not properly trained on what emissivity is. I'd like to talk about one of the common myths of emissivity. The myth is, as long as the material is the same, I don't have to adjust the emissivity in the infrared device to get a proper or correct temperature difference between the two objects. That's actually a myth. And in other words, if I illustrate this, let's say that we have 3 electrical bus bars, energized bus bars with connections. They're part of a 3-phase setup. Each bus bar has an electrical connection, a bolted connection that we're trying to observe with the infrared camera. Reality is that the left bus bar actually has a resistive issue and has increased or gotten hotter. Let's say that it's really 150 degrees Fahrenheit, and the middle and the right bus bar are normal temperature at 80 degrees Fahrenheit. That's a 70-degree rise. With the myth, that means that the infrared camera could just go out there and look at these 3 copper bus bars and see that this bus bar is 70 degrees hotter than these 2 without adjusting the emissivity. That's not true. The camera, if the emissivity is not set for copper, might see this one hotter than the other 2, but it would see it at a much lower temperature rise than it really is. Let's demonstrate this physically so we can have a better understanding of why this is a myth. Remember, emissivity must be adjusted even when you're taking temperature rises or comparison between objects that have the same exact material. The demonstration of the myth that emissivity is not important when performing temperature difference measurements. I have pieces of aluminum. One is heated up on a hot plate, one is room temperature. According to the infrared camera, when I have a temperature spot on the aluminum on the hot plate, I have 81.5 degrees. On the aluminum that's room temperature, I have 75 degrees. So in the camera's mind, that's approximately a 6 or so degrees Fahrenheit temperature difference. My emissivity is not set for aluminum, however. It's actually set for electrical tape or insulation tape. At this time, I'm going to take the spots and move the spot to the electrical tape. So spot 1 to the electrical tape on the block that's been heated, and spot 2 to the electrical tape on the one that's room temperature. Now you can clearly see that with the proper emissivity set for the vinyl electrical tape, we have 178 degrees on the heated one and 74 on the room temperature. That is a temperature rise of over 100 degrees Fahrenheit. Initially, my camera only thought that we were dealing with a 6-degree rise. In reality, it was 100-degree rise. Now, to do this one other way, if I physically move the temperature spots back over to the aluminum and then adjust the emissivity, you can see that as I adjust the emissivity lower, my temperature rise starts to become clear. So even when trying to get the proper temperature difference, I need to set the emissivity to the correct setting. And there you can see that our emissivity is down around 0.05, and we have a more correct temperature rise between the hot and the cool piece of aluminum. Infrared windows have become more and more popular over the last few years because of several reasons. The first big reason, safety. Now, safety involves being able to perform an infrared survey on electrical switchgear with an infrared window in place and not have to pull the cover off. Now, there is another common myth out there that an infrared camera can actually see through walls or see through a thin piece of metal such as this. So why can't we just take an infrared camera, leave the panel covers on, and perform the survey? Well, let me show you why. In front of me is a little disconnect. This disconnect has a resistance inside of it generated by a little resistor that I have in place. As you can see from the infrared camera's image, on the outside of the cover, it doesn't appear to be that there's anything warm inside of this cabinet. If I open this disconnect, and this is not truly energized, it actually is a laboratory experiment. But you can see inside this little cabinet right here, this little disconnect, is an actual hot spot, a heating source. From the outside, we couldn't see it at all. On the inside, we can see it. So without the covers opened or removed, we're not going to be able to use the infrared camera to perform the survey. You might think that, well, we have infrared windows or we have windows already installed into the switchgear, pieces of plexiglass or even glass in some cases. Well, these right here are nice and clear. This is a piece of plexiglass. But if we look back at the infrared camera, a piece of plexiglass is something that the camera cannot see through. An infrared window has to be made out of a special material. Some certain polymers, certain crystals. An infrared window is made out of a material that the camera actually can see through. The infrared window that I have installed onto the switchgear is made by Iris, and it is a polymer. It's a type of plastic that the infrared camera can actually see through. So when performing an infrared inspection, normally you'll come up to the cover will be locked shut. The infrared technician will open up the cover and be able to take the camera and look through the window at the actual issue. The next thing I'm going to do is physically demonstrate how this infrared camera can see through this window. I'm going to use a slightly larger infrared window so that it shows up easy on the video camera. But here's the infrared lens with a cover installed, and then opening up the cover, and the camera can see through the lens. I'm going to use a larger infrared window for this demonstration just because it'll show up better on the video camera. With the cover in place, you can't see anything. With the cover removed, there's our target. So the infrared camera actually has a path to see where the hot spots are without having to remove the cover. Much safer way to perform the infrared survey and leave the covers installed. Now, like emissivity, infrared windows also have a value called transmissivity. Transmissivity, by definition, is the ability of light to pass through something. An example would be visual light is transmitting through a piece of glass. That's why we can see through glass. Of course, infrared light that our infrared camera can see cannot go through glass, so therefore we have to use other materials. This polymer is transmissive for the long-wave infrared camera that we're using. But that means that some of the infrared gets through and some of the infrared doesn't. In order to measure accurate temperatures through an infrared window, the technician has to be properly trained on how to set the camera and its object parameters to get a corrected temperature. Now, if we look at the infrared camera image right now, the infrared camera image shows us reading a temperature of about 148, 149 degrees. If we place an infrared window in the path, we can still see clearly, but our temperatures have dropped significantly down to about 111 degrees. In actuality, the temperature is right around 149, but through the infrared window, we're having an inaccuracy because of the transmission loss. So an infrared camera operator has to set up the camera to properly measure the temperature through the infrared window, or else your temperatures and your temperature comparisons are wrong. 154 degrees with a direct line of sight to the target. When we place the window in the path, we can still clearly see the target and see that it's hot, but we're only reading 113. So about 154, 155 to about 113. The camera operator would know that he needs to adjust for the infrared window. And those adjustments are made inside the camera's brain. Once they have everything set, looking through the infrared window will give them accurate temperatures and accurate temperature comparisons. So to summarize, we talked a little bit about infrared, what it is, where it comes from. We also talked about a couple of advanced topics such as emissivity and infrared windows. When it comes to emissivity and infrared windows and the term that I use, transmissivity, you could probably tell that this is a very, very large subject. And I've only just barely touched on it. To get the full effect of infrared science, infrared level 1 training is the start. Infrared level 1 training takes a full 3 to 3.5 days. Make sure that your infrared technicians that are performing the surveys in your facility have at least a level 1 certification and are properly trained. Or else you could have temperature measurement errors that are very large and they don't know why.